Hello, and welcome to the Joy of Abstraction Book Club, Chapter 6. Thank you for being here, and thank you for submitting some really great questions again. And thank you to the Topos Institute for hosting and sorting all of this out. I am glad that it seems to be of help to people, and I'm enjoying it myself. And today we've got some huge questions. I'm going to start with some huge questions. The first one, what does it mean to understand a formal definition? Crikey, what does it mean to understand a formal definition? I feel like this could be an entire book. Maybe it'll be a book. Maybe this will be a book. Probably someone's already written this book, but maybe I'll write a book about it differently. What does it mean to understand anything? I mean, there's different levels of understanding, right? And I think this is one of the big points about math and about why some people feel like they're not math people, because other people go around saying they understand things or that they're easy, whereas then some other people, like me, always feel like we don't understand things. And that can make it feel like you're not as good at math if you feel like you don't understand something. But actually, maybe it's just that you're seeking a deeper level of understanding than the people who claim they do understand things. And therefore, maybe that means you're actually a better mathematician, not that everything has to be a competition. You know, we don't have to put everyone on a one-dimensional hierarchy about who's better at whom than math. But if I think about what do I mean when I say I understand something else? You see, I don't think I say that generally very much. I think I'm usually a bit more specific, like I understand why something has happened. I understand why somebody does something. I understand why somebody thinks the things they do. And so for definitions, I suppose I would say, try and be more specific and say, I understand how to use this definition. I understand what the point is of this definition. I understand what the ideas are behind this definition. I understand why this definition is stated the way it is. I understand how the people who made this definition came up with it. And maybe understanding a definition is all of those things. And so this question went on to say, sometimes it seems it isn't until trying and failing to solve problems that we learn how to work with the definition. So I would say that you can definitely learn how to work with the definition without understanding it. And I'm pretty sure, in retrospect, that when I used the epsilon delta definition of continuity as an undergraduate, I was very, very adept at using it. In fact, I was so good at real analysis. I did best on that out of every subject in the second year. I didn't really like it, but I did really well on it. And I think I only dropped 1 mark or something. I did much worse at complex analysis, but I don't think I really understood the definition until I had to teach it. And then I had to understand it at a different level. And what I mean by that is, I don't think I understood where the definition came from, why it was needed, why it was set up the way it was, and why it was brilliant. And for me, that definitely meant I couldn't reproduce the definition when I'd stopped thinking about it. And what I mean by that is that when I sat down to teach it for the first time, which was, let's see, about 10 years after I had when I had taken the undergraduate course, I sat down to teach it, and I could not in any way, I had no recollection of what the definition was, none at all. Whereas after teaching it and understanding it enough to explain it to other people, I'm pretty sure that I will now be able to produce that definition off the top of my head at any point for the rest of my life until I lose my mental faculties. And that's not because I remember it, but it's because I understand where it comes from. And so I would be able to construct it for myself based on my understanding of what it's doing and where it comes from. And so I don't think that that's anything to do with learning how to work with the definition. actually, because understanding the definition and then being able to do things with it are really very different things. And that's an interesting point, actually, because some definitions are much better for increasing understanding than for working with at all. And that's something that I'll come back to in the book when I talk about coherence theorems. And so definitions have a different point, and not all definitions are there to help us solve problems. Some definitions are there to provide insight about a situation. And as you may have noticed, my point of view on category theory is a lot about that. I personally don't prioritize the solving of problems. I prioritize the illumination and the insight. And so I would say that the different aspects of understanding a definition are, first of all, that there's different levels, right? And so first of all, there's just, do you follow how the pieces fit together? There are some definitions I read which have so much formality coming out of what appears to me to be nowhere that I just can't even follow the steps of the definition. And maybe I can follow each step by step, but I have no idea where we've got to at the end of it. And I find that very disconcerting. And so I have a lot of sympathy for people getting lost in formal definitions. And I always feel like I prefer the ideas. And so let's see if I can spontaneously come up with a theory of understanding of definitions. I would say, first of all, there's just being able to understand what the logic is saying in the first place. And then secondly, there's being able to see what the ideas are. That doesn't necessarily come after the previous one. I'm just saying things. So there's understanding what the ideas are. And then, of course, there's understanding how those ideas match with the formal definition. So, for example, for the epsilon delta definition of continuity, if you've heard of it, it's got a whole load of symbols, but the idea is a different thing. The idea needs to be matched up with the symbols. So then I would say that there's also understanding how you would come up with that definition yourself. What led to that definition? Why it needs to be like that? And then there are ways of sort of symptoms of understanding a definition, such as, can you understand, do you know why all the pieces of the definition are like that? Can you think of how to generalize it? Do you know how it relates to other definitions? And then also, can you use it? Can you use it can you argue with it? Can you find examples of it? I do remember when I was applying for PhDs, I was doing part 3, the master's thing in Cambridge, and I had written an essay about braided monoidal categories. And I had an interview at Oxford for PhD place, and I didn't want to go to Oxford. I wanted to go to Cambridge. But I dutifully went for this interview at Oxford, and I can't remember, I should probably not say who interviewed me, but they asked me a very basic question about braided monoidal categories. And I had absolutely no idea, because it was a question about an example. It was about vector spaces. And I could manipulate the definition of a braided monoidal category. I could prove coherence for it. I wrote a master's thesis about tortile tensor categories, and it was very technically difficult, and it was about coherence for them, but I didn't know a single example. Now, did I understand the definition, or didn't I understand the definition? I would say I understood the definition. I just didn't understand any examples, not a single one, other than the free ones, which I think are perfectly good examples, but most people don't. Anyway, I think that's probably enough about that now. Oh, wait. With an abstract subject like category theory, how do you practice using definitions to confirm that you understand them? That's a good question. I think maybe I have covered it, because maybe it goes back to whether what you think a definition is for. If your aim is to use definitions to do things, then you need to practice using them in order to do things. But if that's not your aim, then that's not really the point of knowing if you understand something. How can you tell if you understand something? And I suppose for me, it's less about practicing using them and more about asking those questions. And actually, most of all, it's about whether I can explain it to somebody else. So I would say, can you explain this definition to someone else? Can you explain where it comes from, why it's there, and what it's trying to do? Okay, next question. The way that mathematicians use formalism to compress complicated ideas feels similar to how organisms compress information to efficiently navigate their environments. How does category theory help us efficiently navigate the environment of mathematics? Well, like that, I think. It is not necessarily about compression, but about linking things together. I always think it's like taking a lot of disparate information, finding a way to link it together so that it's now a single structure of linked information rather than a whole load of separate information. Because once it becomes a single structure of linked information, we can treat it as one thing rather than a whole load of things. And that therefore, it doesn't take up so much space in our brains. Now, with category theory, it's not just about compressing things, it's also about finding some similarities between different situations so that you don't have to do the thinking over and over again. So once you've heard of the concept of a monoidal category, for example, if you find that something else is a monoidal category, then you can sort of lump it together, not lump it, but you can immediately understand that thing via all the things you already know about monoidal categories. And you don't have to do it all over again. And so it's like the fact that I'm sitting in the kitchen staring at my dishwasher. And so I was just about to say that it's like the fact that once you've understood one dishwasher, you can kind of probably use any dishwasher as long as you understand the principle of dishwashers. And that's the kind of thing that it's probably much harder to get AI to do, because we have to think about how we humans understand the concept of a dishwasher rather than just an individual dishwasher. And I suppose that also depends on who you are. So some people are less comfortable with machines, and so they would find it extremely difficult to operate a different dishwasher from the one that they're used to. And I suppose that's like just with computers, that people who are very uncomfortable with computers can only use their own computer. And then if they were faced with another computer, they would have no idea what to do. Whereas people who are more comfortable with computers can sit down at any computer and sort of mostly use it. And I don't mean at a profound level, I just mean at all. So I think that's what category theory does. It says, let's get familiar with concepts at a certain level, like the concept of a dishwasher rather than individual dishwashers, because then when we go and see things like that, we can feel comfortable with them without having to do that work all over again. Another question, does category theory run into the same sorts of paradoxes as set theory, for example, Russell's paradox? So if you don't know what Russell's paradox is, don't worry about it. I'm going to get to that in chapter 8. So the answer is yes, because categories involve collections of objects, they run into everything that set theory runs into. And Russell's paradox is a very famous paradox in set theory that is resolved by having a hierarchy of different levels of things like sets. So that will come up in chapter 8. Yes. Okay, good. So now some specific questions. On page 74, could I clarify what I had in mind? On page 74, when I wrote, usually we are specifically referring to a relationship with less than or equal to or less than in it. So on page 74, I say that when I'm talking about inequalities. So I say in math, when we refer to things as an inequality, we don't just mean that they are unequal, because most things are unequal. So I'm not quite sure what this question is asking, because I don't know if I have anything more to say than I say in this paragraph. So then then I say, usually we're specifically referring to a relationship with a greater than or equal to or greater than in. The point is that even if we can't be sure two things are equal, sometimes it helps us to know for sure that one is bigger. And the point I'm trying to make is that when we say inequality in math, we don't just mean that things aren't the same, as I say in this paragraph, because most things are not the same. We're referring to less than or greater than to have a relationship. So we've pinned it down a bit, we just haven't pinned it down entirely. And so I think what I mean is just when we talk about inequalities in math, we are specifically referring to a less than or equal to relationship, not just is not equal to. Okay. Why is the triangle inequality important? What breaks if we drop it? The triangle inequality, it's not exactly that it's important, it's that it's there a lot. And when things are there a lot, then it's worth focusing our attention on them, because then we can understand a lot of situations at the same time. And so it's like saying, why are numbers important? Well, it's not that they're important, it's just that they're around a lot. And since they're around a lot, we might as well understand them separately from their environment so that we can then understand a lot of environments at the same time. So I suppose maybe what I mean is the triangle inequality is important because it's around a lot. And because there are a lot of distance-like situations where the triangle inequality holds. So the next part of this question is, what breaks if we drop it? And I Googled this, honestly, and I say this not to tell you you should have Googled it, but to try and help you understand what things are Googleable so that you can then Google them yourself in order to learn things. Because there's been a lot of discussion in various parts of category theory this month about how to give people an opportunity to ask questions. And I will say that Google is really helpful. You can, if you figure out how to Google things, you can get a lot of questions answered. And so for what breaks if we drop it, I can never remember quite what all the terms are for the different ways of dropping conditions on metric spaces. So I looked up something like metric space without triangle inequality, or maybe what happens if we drop the triangle inequality. And the internet must be true because it's on the internet. The internet told me it's called a semi-metric. And the thing is that the reason that the triangle inequality is often true is because it says if you're going from A to B, we could go via somewhere else. And I guess the point is that there are a lot of situations where you can go from A to B via another place, and that should not make it easier. But there are times when it does make it easier, and those situations are a bit different from some other ones. So I suppose there's something a bit more nuanced to say about this, which is that it's not just that the triangle inequality is important, not just because it comes up a lot, but because it represents something fundamental. The difference between when it is true and when it isn't true represents something fundamental. Maybe that's what I mean. So, oh, that's an interesting point. Thank you for asking me this question, which has raised an interesting point, which is that concepts are important if they come up a lot, but axioms are important if the boundary between when they're true and when they aren't is somehow key. I really like that thought. I'm going to have to think about that. Thank you. That's very interesting. So what breaks if we drop it is related to the next question, which is, I try to think about some measures that fail each criterion in turn, but I'm a bit confused. Could you please share some examples? Yes, I could. So I've now remembered that last chapter, there was a question about, was there anything from this chapter that you would have liked to include? but there wasn't space. And I think I would have liked to include this, but there wasn't space. And this is things to think about, 6.1 on page 75. And I didn't include them because it didn't really lead into any category theory I was going to talk about. So where are the criteria? Okay, so the first criterion is distance is a number. So yes, I suppose we could measure. Okay, I'm not sure I can think of one where distance isn't a number. Well, I suppose it could be a collection of numbers. You could decide that you're going to measure distance along two directions at the same time. And then you could have a number, or you could have a matrix of numbers. At a certain point, okay, this is a too profound an answer, but you might have heard of this, so I'm going to say it anyway. If you haven't heard of it, don't worry about it, because I've just got too profound by mistake. But there's a relationship between metric spaces and enriched categories. So an enriched category is when between a pair of objects A and B, you don't just have a set of morphisms, but you can have something else. And if that something else is a number, then you've basically got a metric space. I mean, it's a bit more complicated than that, but if we then if we say metric spaces are related to enriched categories, and enriched categories, instead of numbers, you could have anything as your collection of your measure between two objects. And so in a way, those would all be a sort of distance that's not a number. Okay, criterion 2, distance isn't negative. So what I'm saying is, if we drop that criterion, then it could be possible for distance to be negative. And an example of that is if we're measuring the cost of getting from A to B rather than the distance in meters or miles, then the cost, you might think that it always costs something to get from A to B, but sometimes you might be paid to get from A to B. And there's an example I gave in my first book, I think, How to Bake Pie, where coffee growers are paid to send their coffee to Europe to have the caffeine extracted, because the energy drink people want the caffeine. And that's how we get decaf coffee. And so there, it doesn't cost them any money to send their beans to Europe. They're actually paid. So that would be an example where distance can be negative. Criterion 3 is about 0. So criterion 3 says that the distance from A to A is 0, and that's the only way of getting a 0 distance. So I think I answered this in How to Bake Pie as well. Maybe this is why I didn't include this here, because I knew I'd already done it. So GPS distance doesn't take height off the ground into account. And so if you are both in the same skyscraper, but one person's at the top and the other person's at the bottom, then you're not actually in the same place, but the GPS distance will come out as 0 because it doesn't measure the height. So that's the case where you can be in a different place but still have 0 distance. Criterion 4 is symmetry, and that's where the distance from A to B is the same as the distance from B to A. And it's definitely possible for that not to be true if, for example, you take one-way streets into account. And so if you're driving around a city with a one-way system, at a very basic level, if you're trying to get from A to B like this, and the one-way street goes that way, then the distance from A to B will be quite short, whereas the distance from B to A, you'll have to go all the way around because you can't go backwards up that street. That could also be definitely the case when it comes to cost, because the cost of getting from A to B might be very different from the cost of getting from B to A. It could also be very different if you measure energy expended, because if you're going down a hill, then you don't have to expend energy to get there, but if you're going up a hill, then you do have to expend energy to get there. And the last criterion is the triangle inequality, the one about detours. And so this is related to the previous question where someone asked, what happens if you drop the triangle inequality? Well, I wrote about this in How to Bake Pie as well, I think. My favorite thing that violates the triangle inequality, my least favorite thing, is British train tickets. Because if you want to go from A to B on the train in England, it might be cheaper to go via X. And sometimes it's not necessarily just cheaper to go. It's not that you have to take a detour at all. You just have to buy 2 train tickets. You don't even have to get off the train. You just have to, it's called ticket splitting. And so I used to do this a lot. So there's one example I seem to remember where there was a train from Sheffield to Cardiff, but it was cheaper. I might have got the stations wrong, but there was a train from Sheffield to Cardiff that went through Oxford. But it was cheaper to buy a single from Sheffield to Oxford and a single from Oxford to Cardiff. You could just sit on the same train. And so that violated the triangle inequality. But it's definitely true about, it's more obviously true about the cost of plane tickets, right? It's often cheaper to get a connecting flight rather than a direct flight. So you're trying to fly from A to B, but the direct flight from A to B costs more than if you take a flight from A to X and then another flight from X to B. So that violates the triangle inequality. Okay, right. The next question, hold on a second. Is it possible to use logic to describe aspects of category theory and category theory to describe aspects of logic? Yes, it is possible. And not only is it possible, but it is also done. Is that cyclic? Well, everything is connected, right? So if A and B are related, then you can use A to understand B, and you can also use B to understand A. And hopefully you're not using the same aspects, because if you use the exact same aspects, if you use an aspect of A to understand an aspect of B, and then use that exact same aspect of B to understand the exact same aspect of A, then that does sound cyclical. But what it usually means is that you've used it to understand some other aspect. And if you set up a virtuous circle like that, then you can really build up understanding. I was talking to someone this week who used nature to help develop AI, but then was able to use the AI to help understand nature. And so we actually have to use logic to describe aspects of category theory. We have to use logic to describe any field of mathematics because it's based on logic, but we don't have to use extremely developed logic. We have to use, I suppose, basic logic. Then we can use category theory to explain or model specific parts of logic that use more complicated constructions. So you don't have to understand a large amount of formal logic in order to do category theory, but you do have to understand a small amount of basic logic in order to manipulate mathematics. And by basic logic, I think I mean things like, what does logical implication mean? A implies B means whenever A is true, B is true. The converse is that B implies A, and that's different from A implies B. It's helpful to be able to manipulate things like contrapositives. So the contrapositive of A implies B is not B implies not A. It's important to understand what negation is, because if you can't negate something, then there's probably a lot of proofs that are going to go a bit wrong. You have to be able to be logical. And I suppose, I think it helps to be able to manipulate logic formally at least a little bit in order to be able to be logical. But you don't have to have studied formal logic in order to understand category theory. Is there a way of thinking of one as more fundamental than the other? I think there's always a way of thinking of something as more fundamental than something else. The question is that illuminating? That I've immediately thought of a counterexample to that statement, because I'm not sure it would be possible to think of complex numbers as more fundamental than real numbers. No, I've just thought of a counterexample to that as well. You see, this is what I think thinking like a mathematician is. Just as soon as you say anything, you try and contradict it to see whether it actually isn't true. But maybe let's try again. I don't think that there's a way of thinking of the number 4 as more fundamental than the number 2. Maybe, but maybe there is. And so the important thing is that it doesn't have to be a competition. I don't think that we need to try and put everything into a hierarchy of what is more and less fundamental. People think of things differently. And really everything is related. So I think that, but I do think, like I just said, that because mathematics depends on basic logic, we have to, basic aspects of logic are probably more fundamental than category theory. If pushed to give a definition of basic logic, I don't know if I would be able to. And this is a slightly uncomfortable thing, but if we need basic logic in order to understand mathematics, what do we need to understand basic logic? And I think in How to Bake Pie, I explored this idea and decided that maybe the root of everything for me is modus ponens, which is the thing that says, if you know that A is true, and you know that A implies B, then you can deduce that B is true. And I decided maybe that's the most fundamental thing. Maybe you can't get any more fundamental than that. Or maybe there's a different way of getting more fundamental than that. I mean, some people think that God is most fundamental. And so then I think at some point I decided maybe I believe that modus ponens is God. That went off on a bit of a tangent, didn't it? Okay. Oh yeah, this question is difficult. It's difficult. At the bottom of page 78, I say, we could also say A minus B, but for various slightly subtle reasons, mathematicians prefer using B minus A. Could I please say something more about these reasons? I don't know, can I? So that question is about modular arithmetic and saying A is congruent to B modulo n if n divides the difference between A and B, which I write as n divides B minus A. I don't write it as n divides A minus B. And thinking about the other thing is, I don't know if all mathematicians do that. It's just most of the math I've seen is like that. So it's something to do with difference and distance. And so we like to think of the distance from A to B as B minus A, because if you're going from A to B, you want to measure the amount that you accumulate, what accumulates on the way from A to B. And so what you need to do is see how much you have at B and subtract what you had at A. You don't see how much you had at A and then subtract how much you had at B, even if you're going to take the absolute value, so it doesn't really matter either way. I think specifically for modular arithmetic, it might come down to something in group theory and the formal definition of modular arithmetic as cosets. And this is a bit too much detail now, which is why I didn't say anything more about it in the book, but just in case you know what that is. Oh no, it's way too difficult. How can I explain this? Well, cosets, what you can do you can do something like modular arithmetic when you have, okay, let me try that again. You're taking a subgroup of an overall situation. If you don't know what a group is, this isn't going to make any sense. And you're finding you split up your group into cosets of that probably normal subgroup. And those are called, so if your big group is called G and your small group is called H. Okay, this is not, I'm going to do this. It's not going to make any sense if you don't know any group theory. And this is why I didn't try and go into any more details, I think, in the book, because it just involves way too much lead up. So I think what I'm saying is that if you have H, which is a subgroup of G, then you can look at the cosets, which are things like A, H, and that consists of A is a specific element, and you take all the elements A, H, such that H is in H. And then you can ask yourself that the point is that two cosets, A, H, and B, H, are either completely the same as each other or they're completely disjoint. There's nothing in between. And you can tell when they're the same because they're the same if and only if. Well, what you do is you kind of take the A over there, and so what you need to know is that A, I hope I'm doing this right, I haven't thought about this for years. If A inverse B is in H, and the idea is that you've taken the A, you sort of left multiply by A inverse, and so you end up with an A inverse and a B. And if we're doing subtraction, then what that's saying is B minus A. And in the case of modular arithmetic, we're starting with the integers, and we're taking a subgroup, which is n. It's n times the integers, so it's all the multiples of n. And we put this relation on it, and the cosets then give us modular arithmetic. So it really doesn't make any difference because we could have left multiplied by B inverse over here instead, and then we would get B inverse A. But I think because of the distance thing, for me anyway, I shouldn't speak for, it's better for me not to speak for all mathematicians, but for me, that's why it feels better to me to say B minus A rather than A minus B. Okay, let me see whether I still need this whiteboard. No, I don't think so. So the next question is about page 79. Could I please say something more about the difference between if and only if in a definition and if and only if to declare pre-existing things logically equivalent? So what I said on page 79 is to do with the fact that I use the double-headed arrow sign for if and only if, but I don't do that in definitions. I like the clarity of the symbol when I'm deducing things, but I don't like it in definition because in a definition, it's not a symmetrical situation. The double-headed arrow thing helps to emphasize that the logic is flowing in both directions, that if you start with the thing on the left, you get the thing on the right. And if you start with the thing on the right, you get the thing on the left. Whereas in a definition, the flow is only going one way, really. In the sense that we're deciding what some word means. We're saying, here is a new word, and here is what it means. And so in a way, we're not saying if and only if. We might be saying, this is exactly what I mean by this word. But a precise way of saying that is that this word holds exactly whenever this stuff holds, which means that I'm going to use this, I'm sort of saying, I'm going to use this word whenever all of these things hold and never else, which is expressed by saying if and only if. I'm going to use this word if and only if these things hold. But I'm not making a logical, I'm not declaring that there exists a logical equivalence between these things. I'm giving precise conditions under which I'm going to use this word. And that's why I think it's different. And finally, thank you for talking about what a lemma, a proposition, and a theorem are in relation to each other. What is a definition? Good heavens! This chapter has provoked some very deep questions. First, we had, what does it mean to understand a definition? Then we had, what even is a definition in the first place? Is it an axiom? So an axiom is a basic truth in a world that we're not going to try and prove. We're going to use it as a starting point and see what happens. I think a definition is slightly different from an axiom. I think that in formal logic, it's very different because an axiom is a statement using terms in your system that you are going to assume to be true. Whereas a definition is really just an introduction of a piece of terminology. you could call it an axiom, but it would need to be in a broader sense, because you would have to have introduced whatever word you're defining, you would have to have introduced that somewhere. And this is possibly something that happens in perhaps things more like type theory. I don't really understand type theory, so I don't know. But when you're defining a word or a term or a concept, what you're really doing is saying, I'm going to use this shorthand for that situation. And that doesn't really change the logical structure of a world. Axioms set up a logical structure for a situation, but definitions don't really change the logical structure. They just make a shorthand for something that is there whether or not you give it that name. And so it's like, axioms are like rules in a game. And so, for example, there is a rule in chess about pawns being able to take pieces by moving diagonally across them under certain circumstances. And I believe it's so that if a pawn can start moving by moving 2 spaces instead of 1, but it's not allowed to do that to escape being captured. And so if it would have been captured by another pawn without it, so there's basically this scenario in which a pawn can capture another pawn in a slightly unusual way. And that has a name. And so the definition, you can define that move, right? So you define en passant to be that move, but you could make that rule whether you made the definition and called it en passant or not. And so even if you didn't, so that's a rule and a definition. Was that clear? I'm not sure that was clear. Let me try again. So the concept of 1 + 1 exists. If you have a number system, the concept of 1 + 1 exists. You can define 2 to be 1 + 1, but it's not really an axiom, because 1 + 1 is 1 + 1, regardless of whether you call it 2 or not. And so 1 + 1 = 2 is not an, I would say it's not an axiom, it's a definition. Now let me think about whether I really mean that or not. Is there a sense in which 1 + 1 = 2 is an axiom? I mean, I suppose it depends how you define the numbers, because if you did it another way around, then 1 + 1 = 2 could be a result, because in set theory, 2 is defined to be a set containing 2 elements. So in formal set theory, 0 is defined to be the empty set, 1 is defined to be the set containing the empty set, and then 2 is defined to be the set containing 0 and 1, those 2 sets. And so then you have to define addition as a separate issue, and then you would have a result saying that 1 + 1 = 2. So there it wouldn't even be 1 + 1 = 2 would be a proposition. But the definition of 2 as the set containing 0 and 1 would definitely be a definition and not an axiom, I think. So in conclusion, I think definitions are different from axioms. And I think that is all the questions. There was some appreciation at the end. Your book ignites a lot of curiosity in its readers. Oh, thank you. I'm so grateful that you're happy to entertain those questions that it sparked. Well, thank you for the questions, because I said to someone this week, I think learning and teaching are the same thing. And they said, what do you mean by that? I thought, crikey, what do I mean by that? But I think they are the same thing, or rather the act of learning and the act of teaching can't be separated out. And not just because you have to teach somebody who's then learning, but because you learn so much by teaching. And I've had such interesting thoughts just by answering these questions today. So thank you for that. Thank you for doing this book club. Well, thank you for being part of this book club, because there would be no book club without you reading the book and asking questions. And someone else said, I've been greatly enjoying this book club. Thank you so much. Well, I am glad. I've been greatly enjoying this book club as well. So thank you so much. Thanks again to the Topos Institute. And I hope to hear your questions next week. Bye.